If you've just walked in the room, can you please find a seat as soon as possible? We'd like to kick off real soon now. Quick. Run, run. Yes. Okay, it's time for the second last of the session talks here at PyCon 2017. Our presenter is Sam Kitajima Kimbrel, who is going to tell us about one data pipeline to rule them all. Please make him welcome.
All right, thank you, Chris. So I will start this with a poll of the audience. Please put your hand up if you have data. Great, for the video, that was most of the room. Keep your hand up if you know all of the data sets that you have, how they're accessed, how they arrive at all the storage systems they live in, how to combine them to drive new data or analyses. For the video, there are approximately one hand, 2, 3, okay. Hi, I'm Sam. I lead the data platform group at Twilio, where we build and maintain a unified system for storing, retrieving, and doing computation on all of the data generated by all of Twilio's product systems. I'm going to start with a story. So let's make up a team. Team A's relational database. They set it up to store some data that's generated by their application, and it works great. Until the end of the quarter rolls around, and Team A's product manager wants to run queries to figure out how much their usage grew over the last quarter. And since this database was built for online processing, transaction processing, single row transactions, these giant queries summing up millions of rows are very slow. And the product manager says, can we put the data somewhere else that would make this analysis faster? And so now we have a data warehouse. If you don't know what ETL stands for extract, transform, load, and it's basically the pattern of picking up data from one system that's stored in one format and transforming it into another schema potentially, or another storage format that's better for some other workload, like running analytics queries. So we wrote a Python script to do this ETL job, and took about an afternoon maybe. We have a column store warehouse that's great for running those giant roll-up queries, and it works pretty well. So team B comes along and says, hey, your data warehouse looks really cool. Can we put some stuff in here? And so they, or you, the newly appointed custodian of the data warehouse, welcome to your new job, write another cron job to run a slightly different Python ETL script and copy their data in as well. And so we're doing OK. But then somebody on Team A decides to change some piece of the schema to support a new feature. But everybody forgets about the data warehouse until 1 week later, when somebody on the accounting team, and oh, by the way, when did you start using this, says, hey, why isn't the reporting warehouse updating? Well, crud. Somebody updates it and life goes on. Team C says, hey, we've got this Cassandra cluster that we want to dump into the warehouse. Could you help us? Team D, we want to do real-time spam detection, but run nightly training jobs for our model over all of the historical data. Team E, Ken has full-text search. And just like that, our ETL flow that started out as a couple simple Python scripts is not quite so simple anymore. We have a bunch of cron jobs that are moving data into our warehouse from all these different systems, something rigged onto the side to do real-time stream processing on the data we need to do that for, and we're running flat out just to keep up with schema changes. And then finally, the accounting team comes back. Why don't these two systems agree on how many API calls or page views or whatever is it that we did last month? Wow. OK, so that story is pretty abstracted, but pretty much all of these things have happened to us over the years at Twilio with our data warehousing systems, and I bet they're familiar to a couple of you too. So what happened? From a 10,000-foot view, we had everything working more or less with our data warehousing systems, but it was costing us a lot in developer time and machine time. When we look back at our infrastructure, kind of the legacy systems, we were able to identify a number of high-level problems with this. So first up, we had multiple systems to use as data sources. We had multiple data sinks, places we wanted to get to. And there was some code reuse, but every new type of system required major work to add. And even new data sets from systems we knew about had to be hand configured. We weren't quite at the worst case, but the growth trend is clear. If you have n independent systems to be connected one by one, the connections grow as n squared. Additionally, we had no single source of truth for data schemas. So changing them was risky and required manual work to verify that things were working correctly. And finally, we had no way to guarantee that all the data was correct in all the systems it was supposed to appear in. Network and host failures, as well as programming errors, could manifest as data being wrong in one system or another. So with that as kind of our problem space, what do we want our replacement architecture to look like. We looked at what the industry giants like LinkedIn and Netflix were doing. We looked at our own capabilities, the number of people we had, the amount of machine time we had. And this is what we came up with to guide our architecture as we rebuilt it for developer productivity, scalability, and correctness. So first up, we concluded that there should be one and only one way to publish data into the new platform from any application generating it. A lot of our prior headaches were brought on by inconsistencies in how we move data between systems and having to duplicate effort across them when we made changes. So that had to go. We needed a single system to be the canonical path for records, regardless of how many places they had to be written to or how many they came from. On the flip side, given that we needed to put the same data in multiple storage systems to support all the ways we wanted to access it, we couldn't dictate a single method to get data into them, but we did feel it was important to provide common libraries and tooling to share as much of that logic as possible. We also wanted common schemas. I'm going to go into a lot of detail on this later, but for now, I'm just going to say that it's really easy, a lot easier to ensure that everything works well together when there's a single authoritative source of what constitutes a valid record for any given type of data. And finally, we wanted a way to make sure that all of the systems that purport to contain a given data set have the same data. If a record is present and correct in one system, it needs to be the same everywhere else that it's expected to appear. So since the title of this talk includes the words data pipeline, you might have guessed that we chose to build an event pipeline architecture. From 10,000 feet up, it looks something like this. In an event sourcing architecture, all data is modeled as an ordered series of events that happened. For log structured data, so web requests, ad clicks, API calls, this is a very natural model. For data where records change over time, so configuration data, things that change state, it requires viewing your records as an ordered sequence of change events to those underlying rows from which you can reconstruct the original data set at any point in time. So we have some source of events. Let's call it a web server, and it's handling user requests, and it generates a log event every time a user views a page. And for whatever reason, we're interested in storing those and keeping them around so we can analyze them later. That server emits a record onto a system that stores all of the events in the order they were received as a first in, first out queue. And every system that's interested in that type of data subscribes to that single stream and consumes the events in the same order they were published. Important to note here is that the consumer systems and also the producing systems don't have to be the same type of system. One consumer of this data stream could be a relational database providing near real-time access to individual rows, while others could be writing a permanent archive of the data in kind of bulk storage formats to cold storage systems. You could do real-time computation on the stream of data to derive new data sets, and so on. And just like we have multiple systems at the far side of the queue, we have multiple distinct systems sending different types of events to their own streams. And we set up each consuming system to only read out the particular types of events that it's interested in. And so Apache Kafka is the backbone of this architecture at Twilio. Kafka is a horizontally scalable, fault-tolerant, and very high-throughput streaming message platform. If you're not familiar with it, Kafka originated at LinkedIn, and they currently use it to move over a trillion with a T, events per day. It's become wildly popular since going open source and is used by companies ranging from Netflix to Goldman Sachs, and since I'm here talking about it and I work at Twilio, we use it at Twilio. A Kafka deployment consists of a set of broker nodes that host topics, and topics are just those streams of ordered events that I told you about earlier. Brokers accept writes to the topics from producer nodes, persisting the producer events to disk and replicating amongst themselves for durability. Consumer processes connect to the broker nodes, which deliver those events from the topics in the order they were produced. And as they process events, consumers send back acknowledgements of how far along in the stream they are. Basically, this is the event offset. You can think of this literally as a file that you're streaming in. So producers are appending to the file, and consumers are following along behind them, reading from the file. As the consumers proceed through the stream, they commit offsets back to Kafka, so Kafka knows how far along they got. So if you lose a consumer process, if it restarts or dies or it gets replaced, it starts back up. Whatever you replace it with starts back up from the last offset that Kafka had seen committed for it. So in that way, Kafka guarantees at least once delivery of every message sent to a topic to all registered consumer groups for that topic. Kafka is pretty straightforward to operate, but if you're into managed services, Heroku has a Kafka add-on, and Amazon's Kinesis service exposes similar APIs and contracts to what Kafka does. So to recap what we've done so far, to use Kafka as a durable, guaranteed delivery event bus, We treat every data set as a separate topic of events produced by the application systems that generate them, and we connect a consumer as needed for every storage or processing system that needs to read that data. So far, this is pretty standard stuff. You can find dozens of blog posts on this from LinkedIn, Netflix, Confluent, and a lot of other companies. I'd like to go into the things that we learned along the way that are a little less obvious from the blog posts. So first up, and this is the strongest opinion in this talk, so here goes. You should absolutely, by all means, definitely use a strongly typed serialization format with a defined schema and validation library on both sides of your event bus. So to use a story here, there are a lot of systems out there, like MongoDB, for example, that just let you chuck arbitrary documents at them. And this is tempting. You can get started really quickly with these systems, but there's a cost to this. Your schemas and the enforcement of those schemas moves from a single place to many scattered places in your application code. This opens the possibility of sending data or storing it that you can't process later with different versions of the code. So to give an example, if we have an application writing data somewhere and a batch job written potentially in a different language that picks it up and does something with it, let's say it generates a report, if somebody makes a change and removes a field from the data in the producing application without telling the maintainer of the batch job, and the batch depends on that field, kaboom. Now somebody has to go pick up the pieces. Oh yeah, sorry, this is blank because I'm doing a lot of talking. I have no new content for you. So we dropped a field in the producing side, and we didn't bother to tell the person who writes the batch job that generates the reports, and so it fell over. Somebody has to go pick up the pieces, fix the code on the batch, and rerun it. And that's if you're lucky. If you're unlucky, you get a silent kaboom in the form of incorrect, missing, or corrupt data, and let's really hope that that data isn't driving your revenue numbers. So there are a lot of open source libraries for schema validation and serialization. Please pick one and use it everywhere that you transmit data between systems. At Twilio, we ended up choosing Avro, which is an Apache project, for a number of reasons. Avro has official cross-platform support for both the JVM and for Python, and community-supported libraries for just about every other language in existence. PHP, Ruby, Go, anything you want. The Java library, if you happen to use Java, offers both dynamic and static types, so you can just deserialize records to get a map, or you can get actual code-generated Java objects, which will give you static type guarantees if you're using Java, that sort of thing. On Python, basically, you get a map. Or a dict, excuse me. When you're deserializing, the library automatically converts between compatible versions of the same schema. So if you have version 1 of your record schema and you add a field to it that has a default value, or you remove a field that had default value in version 2, it will automatically give you whichever version you want to consume as, regardless of what was actually handed to you in the serialized format. And finally, it offers a compact binary serialization format that doesn't include a copy of the schema tagged to every record. Other systems do this, and so you kind of have that bloat of every record you send down the pipe has the schema tagged onto it. So you have to register your schemas and know about them ahead of time, but the trade-off you get for that is a smaller representation on the wire. So last word here. Enforce the schemas and validate them when records are produced from the applications that produce the records without exception. Doing this gives you an extremely powerful guarantee. Every record coming down a topic is going to be valid for any consumer of that record to deserialize. It keeps the onus of data validation on the producers, where it's easier to test an update since most of your data types are only going to come from one or a small number of code bases, but might be consumed by many more. Within a single topic, you should only make backwards compatible changes to a schema. If you need to break compatibility, start a new topic for the new version. Let your consumers run off the end and then migrate them over. So with those rules and guarantees in place, the worst that can happen if you miss a schema update on the consumer side is that you've delayed how soon the data is available. You can't break your processing and you can't lose data. So the record schema alone is not the only information that's useful to know about a topic and the records in it. So one of the things you need to know is, given a Kafka topic name, what schema applies to the records in it, and what versions should we expect to see of that schema coming down the line. We also might want to know, because distributed systems are tricky, how to resolve duplicates, right? So in the face of network partitions and host failures, we aren't guaranteed that we'll produce or consume a record only once. And what's more, even ordering records can be tricky. Kafka only knows about the order that records arrive at the brokers. So if you have multiple hosts producing onto a topic in parallel, you're going to have to sort the ordering out when you consume. To do that, we need to know a couple of things. We need to know what uniquely identifies a record. And then after that, we have to know what logic we apply to choose a winner or merge conflicting versions of records with the same ID. So another tip here, just for doing IDs and ordering, wall clocks, if you haven't heard, are not to be trusted across multiple hosts, so don't just use the latest physical timestamp. There are things called vector clocks. I unfortunately don't have a lot of time to get into them, but those require some sort of serialization and locking for concurrent operations in the same object. There's a lot of reading about this. I'm happy to provide links to anybody who wants after. And finally, it's useful to know, in addition to how we deduplicate the data set, how do we verify that this data is complete and correct? So we can reuse our source of uniqueness, right, the unique key we specified before on this topic, for a first pass at reconciliation across different consumer systems, right? So count unique is always a good first step. If you've got the same number of records in the same place, you're likely to have the same set of records. If there are additional checks we can form, right, maybe you want to sum up the price of all the widgets you sold, you can do that, right? So you can specify an aggregate operation to run over a data set and which fields to use it for, and then just verify across all the places you store your data that that matches. So armed with that, I've covered what we started off with, what we disliked about our original systems, what we wanted out of our new architecture, and the core abstractions that you've got in a Kafka-based event pipeline, which is also referred to as a unified log. And next, I want to go into some of the libraries and systems we built to augment our Kafka cluster and connect it to our data systems. So first, we have a metadata registry API. So storing those record schemas that I mentioned and all of the additional metadata about uniqueness, ordering, and correctness in a registry gives us programmatic access to that data from any system that produces or consumes records. So our metadata registry doesn't actually handle any data records itself. It just says, here's the schema for this type of record, and that extra metadata about uniqueness and ordering validates that when you create a new version of a schema for a topic, it validates that the new version is compatible with the old ones, and then just hands that metadata back out to any system that needs it. So for example, on the producer side, you might want to say, am I using the right schema for this topic? So you can validate records before you send them. Kafka comes with producer and consumer implementations for a lot of programming languages, but like Kafka itself, they work on the level of byte streams. The Kafka brokers don't know anything about our schemas. They just view every record as a chunk of bytes. So we built a wrapper around the Kafka libraries for systems that need to produce to handle that serialization and validation step. So the producer library accepts the Avro record object, validates that it conforms to the schema for the topic you're trying to put it onto, and serializes it for you. The consumer library basically does this in reverse, right? It says, oh, you're consuming this topic, looks up the schema for that topic, and then deserializes the records using the appropriate schema, and gives it back a native object or a dict for your application code. Twilio has an extremely polyglot development environment. We run a lot of Python, a lot of Java and Scala, some PHP, and there's even a little bit of Ruby, Node, and Go floating around. Our data pipeline libraries, so the official ones wrapped around the direct Kafka producer library, we support Python and Java, but porting the logic to 4 more platforms would have been a lot of effort for diminishing returns. We also, at Twilio, already have very well-defined and well-supported standards for internal REST APIs with JSON serialization. So we built a simple service that takes that act of producing to a Kafka topic and doing the validation before you do so, and just put an HTTP interface on it. And so anything that is not Python or Java can just throw records at this producer API as JSON, and they get the same guarantees. So that's what we did for actually directly producing and consuming from Kafka. What do we do with everything once you've got the records into Kafka? For us, this breaks down into roughly 6 types of system. So first, we can archive datasets to inexpensive and scalable cold storage. This is S3 for us. So we use this primary archive data to power 3 more use cases. So we can load it into data warehouses for doing analysis on structured subsets of that data. We can run batch processing jobs as part of our engineering workflow, right, to transform arbitrarily large amounts of data into other data sets, derived analysis. And we can do ad hoc analysis of the archive data without needing to load it into a warehouse. Next, we do stream processing. Since Kafka is high throughput and low latency is sub-second, right? 10 milliseconds, 50 milliseconds end to end. You can connect stream applications directly to Kafka and process records in very close to real time. And finally, we can connect traditional transaction processing databases like MySQL or Elasticsearch to provide access to a limited amount of recent data with very low end-to-end latency, single row access, limited amounts of search, but for your online access. So I'm going to go through these in more detail, starting with archival. So our primary data archive is something that we call TwilioFS, which is really a fancy name for some standards we made up about how to organize data in S3. It's essentially a data lake, which is a term that some data architects made up to describe what happens when you dump all of your data into one place so that you can extract it in chunks for further processing or analysis. And that looks something like this. The incoming records from Kafka for a given topic are consumed by a system that we call copycat. Kafka brokers, being a finite set of machines, do not have infinite storage space, and so only retain a fixed window of time for each topic before the data expires and is archived off, or sorry, deleted from the Kafka brokers at the back end. So Copycat has one job, to copy byte for byte entire Kafka topics into Amazon S3. It's a Kafka Connect application. Connect is a framework that's distributed with Kafka, and it's designed for exactly this operation of consuming data from a Kafka topic and writing it somewhere else, or reading data from another source system and producing it into a Kafka topic. And we use Connect for pretty much all of our sync systems because it's just a very easy to understand pattern. Copycat's output is organized by the topic and the partition. So we might have widgets and then partition 3 of the widgets, and then the date and the hour, and then the highest offset in the Kafka batch that's flushed into that file. Most of our copycat consumers basically accumulate about 5 minutes of records in chunks and then just flush those in files to S3. Before we've done anything else with this data, Copycat has already given us a really neat capability. Since the output is a perfect copy, byte for byte, of the original Kafka topic, we can actually just take any subset of that time-organized stream of data and replay it back in Kafka, like we've gone back in time. So this comes up if somebody finds a logic bug in their processing system, for example. They fix it, and then they roll out the new version of that code, and they say, actually, I want to reprocess 3 months. So all we do is go into S3, pull out those 3 months of copycat data, and just dump it into a Kafka topic, and they can reprocess everything without having to deal with going to find that data themselves. But copycat is just the first step. Because its output is not guaranteed to be unique or in order, since we've got producers running in parallel and, as I said earlier, distributed systems, we run a system called copydog to clean it up. It's called copydog because it chases the cat, I don't know. It's a Spark job, and it organizes the raw topic data that Copycat sends to S3. And so this is the first place in our system where that topic metadata really comes into useful about deduplication and ordering as configuration for Copydog jobs. So Copydog uses its knowledge of how to sort and merge records to emit a verified, sorted, and deduplicated archive of each topic's data, also to S3. And so it actually has 2 inputs. One of its input is the latest input file from Copycat since its last run, and then the other one is the existing set of data in the clean output set. So Copydog, first takes a set of new records since the last run and sorts it using the sort key we configured as the metadata. Then it identifies the set of date prefixes for which it found new records in the incoming batch, reloads all of the existing records for those dates, finds duplicates using the configured unique key on the metadata system, and merges them appropriately according to the specified rules. And then finally, it writes out all of the changed date prefixes to S3. And since S3 is almost an HDFS, but not quite, and it doesn't have an atomic move operation, there's actually a system of versioned file names and a metadata file that points to the current version, which keeps other Spark jobs and other downstream consumers seeing a consistent view of the data. We don't update the version pointer until we finish flushing all the files back out. So the output of this is actually our true data archive. Every record produced to every Kafka topic is in this S3 bucket exactly once, in the latest state we've seen for it on Kafka, and sorted according to the specified ordering for the dataset. And the pivotal element of both these systems, in order to make the data platform group go fast as developers, is that they're 100% configuration driven. The logic is reusable across data types, and the metadata API provides the configuration we need to specify the input and output directories, the schemas, and the sorting and merge strategies. We can provision new copycat tasks with an API call to the Kafka Connect group, and copydog jobs just require pushing new configuration into our task scheduler. So this archive of data is now usable for 3 things. First, we can load it into data warehouses for interactive querying. So we use Amazon Redshift as our warehouse engine. Redshift is a managed columnar database that speaks Postgres, so our BI analysts love it. They just write SQL at it. It's compatible with any visual BI dashboard system that speaks SQL, and it's optimized for bulk loading of data from S3. We built a bunch of custom tooling around the management APIs to let us easily provision multiple Redshift clusters and generate schedules based on our metadata to load data from S3 into one or more of the warehouses. Every cluster has a different set of data based on who is using it. So for example, the finance team needs all the transaction data, but engineering doesn't need to see that, and they probably shouldn't. The ops team might want to know all of the phone number configuration data, and PMs probably want API logs. So every cluster has a different subset of the data based on their needs, and this lets us keep those clusters small and performing optimally for those use cases, and like I said, keeps the sensitive financial information away from people who don't need to see it. We can also use our primary archives to drive batch processing for derived data and ad hoc analysis. So this is Spark again. Spark has a very well-supported S3 data driver, and we've extended it to support the organizational and schema metadata available to us. Engineering teams that need to process large amounts of data just write dedicated Spark jobs and use our infrastructure to schedule them, so it's a managed platform that we provide. We also use Spark for ad hoc processing. So I'm guessing most people here are familiar with Jupyter Notebook, but if you're not, it's an open source project for using and sharing interactive data notebooks. This lets engineers and PMs query large amounts of data from S3 without having to load it into a warehouse cluster first. This tends to come up during outage response, where we might find something and say, oh, well, how long has this been broken for? How many API calls are actually affected by this? And we go crunch through six months worth of logs. So outage response, and if you're prototyping, you need batch jobs, right? So you can just write some Spark SQL queries and fire them off and see if you get the right result before you go encode it into a full-on Spark job. And I'm going to sound like a broken record right now, but we also use Spark in streaming mode to do stream processing in real time. So you can connect your Spark tasks in streaming mode directly to a Kafka topic, process the data in real time, and emit results back into a new topic for storage elsewhere, or real-time dashboarding, whatever you want. And finally, we can consume directly from Kafka topics and write the data to online storage systems. And this is about as simple as it sounds, right? So we run a Kafka Connect service that copies data from a Kafka topic into a database like MySQL or Cassandra or Postgres or Elasticsearch as it comes in, and then you can query it in real time from other systems to satisfy user requests. Okay, so we have our data in our pipeline. We've written it down in a bunch of places. We've done some computation on it. How do we know that the data is correct in all the places it has to be? So first off, as I mentioned earlier, Kafka tracks consumer offsets. So as the consumers are processing the topic, they write back to Kafka and say, I'm good through offset 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. And those offsets are themselves available as Kafka streams. So we can build lightweight apps to consume the offset data as it's running through the system and monitor the progress of every consumer group. So if a particular consumer system gets stuck or slows down, we can set off an alert and say, go provision some more capacity here, go fix what happened. For data correctness itself, we use our topic metadata to do lightweight smoke testing. So knowing how to identify unique records with our metadata means that we can ask our data stores to count them up. And we can add additional checks. For example, how much did we make in widget sales yesterday? Or even you can just do a full row checksum to ensure that the different storage systems agree with each other. So that's about it. Let's review. So we've seen how an event-oriented data pipeline architecture built around Kafka as a reliable and high-performance data bus gives us a strong foundation for reasoning about and planning data flows between systems that produce data, systems that process and consume data, and systems that store data. We've talked about why strongly typed data using Avro with a single source of truth for schemas, is important, and why your data processing systems will benefit from that. And I briefly touched on how the properties of these systems both inherently guarantee that data is delivered everywhere that it needs to be, and how to build lightweight monitoring systems to verify that that's actually the case. So let's go back to our story from the beginning of the talk. Instead of that growing web of connections between sources and sinks, we have a single path. Data flows as streams of events through Kafka, and every system that needs a particular type of data can connect and listen to it. When you change the schema, the systems connected to the data seamlessly converts data to the new version they expect, or they gracefully process to the end of the topic with the old version can be updated to pick up a new version. The end of the year rolls around, the PMs just request temporary Redshift clusters to pull in their logs and do the numbers for their slide decks. We try out new data stores all the time. We drop them in as new flavors of data consumers. And you've got that spam detection code that I mentioned in the story earlier, runs nightly as a Spark job, and the same code loads up the new model and just processes the in streaming mode on incoming messages. We hook up Elasticsearch, and everything works great. So that's it. That's all I have. Thank you for listening, and I hope that ESA heard.
Thanks, Sam. We unfortunately don't have any time for questions, but if you do want to have a chat with Sam about some of the stuff he's talked about, he'll be hanging around here for a few minutes, I imagine, and you can come up and speak to him here. We'll be back underway in about 10 minutes' time.